Welcome to the lecture series on soft computing in computer science. In this presentation, what we are going to see is backpropagation neural network. Last presentation we have seen about some basic ANN models like Mekula-Pitts, Hebb, Perceptron, Adeline and Madeline model. For all the models, what we have discussed is architecture, net input calculation, output calculation, weight and bias updation. After having discussed all those primitive models, we discussed about the problem of linear separability. That means most of the real world problems are non-linear in nature, and these primitive models couldn't solve any problems that are of non-linear in nature. In order to solve those non-linearity in case of some problems, real world problems, one can use this particular neural network model for effective results or for wide applications, so on all. So let me go into the presentation. This presentation starts with introduction to the neural network model, its architecture as well as the algorithm. That is the main focus of this particular presentation. So the algorithm is divided into three phases: feed forward phase, back propagation phase and weight and bias updation phase. And overall this algorithm is viewed as a gradient descent approach. And finally this presentation conclude with what are the various design parameters of this neural network model. Let me go into the presentation one by one. This neural network, backpropagation neural network, is the most important development in the era of neural network. Starting from the 1943, we have discussed some primitive models in the last presentation. Until now, there are various developments have been happening in the neural network model. Of those models, this particular neural network model is the major development, or we may say that major breakthrough in the neural network model development. According to architecture, one can call this neural network model as multi-layer feed-forward neural network model. And according to the algorithm, since this neural network model is trained using an algorithm called backpropagation algorithm, this model is going to be either called by the name backpropagation neural network. And of course, the weight updation process as well as the bias updation process follows a approach called gradient descent approach, which we will be seeing it in detail in the subsequent presentations. Architecture. So if you remember the architecture that we have discussed in the primitive models like Mekula-Pitts, Hebb, Perceptron, Adeline and Madeline, all have some unique architecture identity. Apart from the Madeline model, all the other four model, if you could see that it is a two-layer architecture, input layer and output layer. In the input layer you can have n number of nodes, whereas in the output layer you should have only one node. So this is what the case with Mekula-Pitts, Hebb, Perceptron and Adeline model, right? When you discuss the Madeline model, what is the major change is the introduction of a layer in between the input layer as well as the output layer, and it is called as hidden layer. And the training algorithm has been studied under two phases: input layer to hidden layer and hidden layer to output layer. Of course, in the Madeline model also we have only one output node in the output layer, but we can have n number of nodes in the hidden layer as well as n number of nodes in the input layer. When you talk about the architecture of this feed-forward neural network, because of the non-linearity in the problems, they have introduced more than one number of output nodes in the output layer. So if you could see the architecture, it is viewed as a three-layer architecture model where it contains input layer, hidden layer and output layer. In general, you can have n number of nodes in the input layer as well as n number of nodes in the output in the hidden layer. But what about the output layer? In all the primitive models, you have only one node that tries to solve only the linear separable problem, because we can have only two classes at the maximum when you want to realize the AND gates, or when you want to realize any data classification problems. There are only two classes and they are all very easily, that means linearly separable by means of a single straight line. What if you have more than one classes, and what if those classes are overlap with one another? Then this problem is non-linear in nature, and you cannot have only one node to decide the class one with other classes, because you have multiple classes. So here in output layer they have introduced more number of output nodes in order to address the non-linearity in the problem domain. So let us take the diagram first. Yes. So in the input layer, if you see that there is a node, x1 node, etc. up to xi node, etc. up to xn node. That means what it signifies, in the input layer you have n number of input nodes, right? And all the input nodes have connections, and those connections are heading forward towards the corresponding hidden nodes. So x1 is leading to z1, x1 is leading to zj, and x1 is leading to zp. Accordingly, if you could see that the connection will have the different weight values v11. Let me take a different pen color. Right, I can have this blue. See, you have the different weight values v11, v1j, v1p. That means the connection that is going from 1 to p will have a weight value v1p. The connection from 1 to zj will have the weight value v1j. The connection from 1 to 1 will have the weight value v11, accordingly for all the input nodes. This you should remember very clearly. So let us once again recall the connections between xi and z1. So what is the weight values? vi1. Why? It is from xi to z1. vij. Why ij? It is from xi to zj. vip. Why vip? It is from xi to zp, right? So accordingly the connections are there. So what is this v1 to vnp represents? v11 to vnp represents? They are all the synaptic weights between the input layer as well as the hidden layer. And we could notice that there is one bias is there, x0, and it is also denoted as v01, v0j and v0b. So this is the way in which you can study the input connection between the input layer as well as the hidden layer. Similarly, the same kind of connection parameters are available between the hidden layer as well as the output layer. So let me choose a different pen color in order to identify the difference. So if you could see that in the hidden layer, you have the node z1, zj and zp, and each node in the hidden layer is connected to every other node in the output layer, y1, yk and ym. So the node z1 connected to the node y1 will have the weight connection w11. The node z1 connected to the node yk will have the weight value w1k. The node z1 connected to the output node ym will have the weight value w1m. So accordingly you can take all the other nodes of the hidden layer also, zj, zp and its corresponding locations, corresponding weight nodes, right? Here also you have the bias value z0, and that z0 is having connected with the corresponding output nodes via the weight connection w01, w0k and w0m. So this is what the second phase of the input connections between hidden layer as well as the output layer. Let me go into the third phase, for which I will use a different pen color in order to differentiate. So I will use this green color, right? So in the output layer you have y1 node, yk node as well as ym node. right? So y1 etc. up to yk etc. up to ym. That means m number of nodes are there in the output layer. For each output node, you have the corresponding target node T1, Tk, Tm, right? So the output produced by this output node small yn, small yk and small ym has to be made a comparison with the corresponding target value T1, Tk and Tm. And the difference between the actual output small y1 and the target T1 is treated as the error E. And this error is used to update the weight values both in the hidden layer and from the hidden layer to the input layer. So likewise, this process is going forward as direction in terms of signal inputs and backward direction in terms of weight updates, and hence this algorithm is called as backpropagation algorithm. So this is the third phase. So what is the first phase? The first phase is nothing but weight updation between input layer and the hidden layer. Second phase is nothing but the weight updation between the hidden layer as well as the output layer, and the third phase is the error calculation between the target as well as the output. According to that, the weight updation is carried out. So likewise, you should understand this architecture. Let me say once again. So if you look at the architecture, it is a three-layered architecture consisting of input layer, hidden layer and output layer. In all the layer, you have n number of nodes. In input layer, you have x1 to xn. In hidden layer, you have z1 to zp, and in the output layer, you have y1 to ym. Whereas for all the output nodes, you have a target T1, Tk up to Tm. So each input connection has to be think in such a way that it should have a massive parallel connection between every input node to every other hidden node. Likewise, every hidden node to every other output node. In such a way, the connection should be messy form. In addition to the regular inputs, you should also have bias in the architecture, right? So this is what the architecture of a feed-forward neural network is all about. See, the algorithm of this feed-forward neural network had been studied under three phases. In the forward phase, backpropagation of error, weight and bias updation. When you take the case of forward phase, you need to do the calculation of the values both in the hidden unit as well as in the output unit. As I said in the previous presentation, next to architecture, it is the one to understand how the net input is calculated and how the output is calculated, followed by weight and bias updation, right? So in the feed forward phase, net input calculation has to be carried out in the hidden unit as well as in the output unit. Output calculation has to be carried out in the hidden unit as well as in the output unit. So that is in the feed forward. So in the feed forward phase, only the input signals are fed in and the weighted sums are calculated, over which activation function is applied, then the output is taken out. Likewise, in the phase 2, backpropagation of error. So what is calculated? Error is calculated. What is that error? So error is nothing but difference between the target as well as the actual output. Based on the error, you need to calculate the del W and del B. So what is del W? That is change in weight and bias, right? Likewise, for hidden unit also, you need to calculate the net delta input, that is in the reverse side delta input, net delta input and its associated error and its associated weights and bias value change. And in the third phase, the weight updation is carried out both in the hidden unit as well as in the output unit, for which new weight value is equal to old weight value plus change in weight value, that means del W, change in bias value, that is del B. So this is what you need to understand the algorithm. So let me explain this here one by one. So here computationally, when you talk about these layer, you can take this as a different one. Let me take a different pen and I will explain, right? This input layer is just treated as a layer that passes the input signal. So computationally, it is not taken into account because there is no computation happened in the input layer node. It just passes the input signal. Whereas in the hidden layer, if you talk about every node, each node is a computational unit, that means information processing unit, as I explained in the previous presentation. So each node has to be treated as a two partition, right? So one comprises of the summation unit, another one will doing the threshold part. So that means you have to calculate in the net input in the hidden unit as well as in the output unit also you have to calculate the net input as well as the output, right? So this is what the feed forward phase, that is the first phase until this feed forward phase. And here in this phase, what is calculated is, that is error is calculated, right? So based on the error, the weight values are updated in the backward direction. For updating the weight value, first what you have to calculate? Change in weight value, that is a del W here in this junction, del B, del W in this junction, W naught, right? W1 like that and all. For which here in this case, what you have to calculate? Del V1, del Vi, del Vn, del V naught. So those things are calculated. So likewise, the change in error, according to that change in error, change in weight value as well as bias has to be calculated. Then all these has been used, and finally what is calculated is the new weight is calculated. So originally before running this algorithm, this V1 value, V1J, V1P, this Vi1, VIP, so Vn1, all these values are randomly chosen, right? Maybe 0 to 1, any value between 0 to 1. But while after calculating the error value between this actual output as well as the target, so what is calculated is, what is updated is the weight values are updated. That means V1 values are updated between X1 and Z1, W values are updated between Z1 and W1. Likewise for all the nodes of the hidden as well as the input layer nodes. So this is the process. So again I am illustrating the phase 1. What is the phase 1? It is a feed forward phase. In the hidden unit, what is calculated? In the hidden unit, net input is calculated. So how to calculate the net input? So the net input is calculated based on the formula that is already we have discussed. So the net input is calculated like this. That is, here you have a bias plus summation I equal to 1 to n xi Vij, because the weight parameter notation given is V. So V1J. What is output is calculated over the net input. What is the net input? Z in J is the net input. Over the net input, you have to apply the function, activation function, in order to calculate the Zj value. Likewise for output unit. Output unit, you have the WOK, that is bias value, plus Zj is equal to J equal to 1 to P equal to Zp Wjk. So likewise for net input. So this is the feed forward phase. Next, phase 2, that is a back propagation of error. So what you have to calculate? You have to calculate the error. So this you remember, right? In the previous presentation, del k is nothing but the error between tk minus yk. This is nothing but error. And over which the derivative of that y in k has been calculated, f dash of y in k. According to the del k value, that is a dou k value, according to this dou k value, this del w value and the del w0k value has been calculated. That is change in byte value has been calculated. The same thing is applicable in the hidden unit also, for which first the net delta input is calculated, and that net delta input has been used in the error calculation, and that error can be used in the calculation of change in weights and bias, that is a del Vjj and del Voj, that is has been calculated. So this is the calculation of error in the back propagation phase, that is the phase 2. Then that weight and bias value has been utilized to calculate the new weight. So what is new weight? The new weight is equal to old weight plus change in weight. Likewise for hidden unit, weight and bias adjustment. The new weight is equal to old weight plus new weight, change in weight value. So this is the third phase. So let me summarize once again. The back propagation algorithm comprises of 3 phases. Phase 1 is the feed forward phase. In phase 2 is the back propagation error. Phase 3 is the weight and bias updation. In phase 1, we need to calculate in the two stages, hidden unit as well as output unit. In hidden unit, net input is calculated and then output is calculated, as well as in the output unit, net unit is calculated and output is calculated. So for all the calculations, this presentation has given you the corresponding mathematical expression. So mathematical expression has been used in order to calculate the net input as well as for the output. Likewise, for back propagation of error also, you need to calculate the error in the output unit and you have to calculate the change in error weight value. For the hidden unit also, you need to calculate the net delta input according to this expression, then the weight of error is calculated, then the change in weight is calculated. After having calculated the change in weight and bias value, in the third phase, you need to calculate the new weight, that is new weight is equal to old weight plus change in weight value. So all these expressions are very essential in order to understand the algorithm completely. So what is this algorithm overall says that? This algorithm says that you need to calculate the net input and you have to calculate the output and you have to calculate the error, and based on that you have to update the weight. So these are the 4 things that you need to remember in a neural network based training algorithm, and this is the algorithm that is widely used, and this algorithm is a very breakthrough in the further development of artificial neural network model until now. And if you see that this approach is a gradient descent approach. That means if you could see, so there is a weight vector that we have chosen initially. Initially, if you could see that the weight vector is chosen in such a way that the error is 15 in terms of error in terms of x-axis, and in terms of other weight value is error value is 1. But over the period of time, if you could see that, the minimum error we have obtained at this point. At this point, if you see that the weight value is here, the W0 is here, and we have obtained the very minimum error. So originally the error is this much huge amount, but over the period of iteration, that is both in the forward phase as well as in the backward phase, calculating the change in weight and bias value, updating the new weight and bias value, and we are going back and forth between forward and backward direction. At one point of time you will attain the minimum value. At that point you have to calculate the corresponding W0 as well as W1. So this is the way in which you need to approach the gradient descent methodology for calculating the weight values, that is initially started by a random manner, and over the period the weight values are tuned and updated according to the error value. A summary of this presentation again. So where we have started the presentation with the definition of the backpropagation neural network. So what is backpropagation neural network? It is a 3-layer or n-layer feed-forward neural network trained by an algorithm called backpropagation algorithm. Why it has this backpropagation? Because this algorithm can be explained in terms of both in the forward direction as well as in the backward direction. In the forward direction only the input signals are giving out, whereas in the backward direction error is calculated and error is fed back. The error is fed back, and that error value is utilized to update the weight value. Of course, weight updation is nothing but the learning in the neural network. So in order to understand this process once again, see the weight values are fed back. So if you look at it, the architecture is forward, not in the backward. There is no connection is there in the backward direction. All the connections, all the arrowheads are in the forward direction only. Then what is backpropagated? Logically, it is the error value that gets backpropagated in order to update the weight value. That you should remember very seriously. Only the connections are in the forward direction, whereas logically the error values are backpropagated in order to update the weight values. That means in order to make sure that neural network learning is happening, the weight values are the error values are backpropagated to update the weight values. That is nothing but learning in the neural network. Coming to the architecture, accordingly the architecture is designed. You have roughly 3-layer model, input layer, that is not a computational layer, hidden layer, that of course a computational layer, and output layer, where which you are going to compute the output. So that output is treated as actual output designated by the symbol y1, y2, yk, etc. up to ym, for which you have a corresponding target tn, t2, t3, etc. up to tm, tk, right? So we have to compare these two, you have to calculate the error, and accordingly it has been fed back. So that is a detailed analysis we have presented with respect to the architecture. Then with respect to the algorithm, we have gone to phase by phase manner. In the first phase, it is treated as a feed forward phase, giving only the input signal. That means the calculation of net input as well as the calculation of output. So calculation of net input has been conducted with the general standard formula, and the calculation of net output, so the calculation of output can be conducted with the help of activation function, right? Then the error is calculated in the third phase, right? So the algorithm is illustrated with respect to three phases: feed forward phase, back propagation of error, and the weight addition phases. And finally, it is a small glimpse of idea what is meant by gradient descent approach. What is meant by gradient? The gradient is nothing but the error, and the descent, the error is reduced over the period of iterations. So initially you have to start with the random weight values, and this random weight values has been updated over the period based on the error, with the goal of reducing the error to the minimum level. So that's the idea behind the gradient descent approach, and this was what visualized to you. So in the next presentation, what we can see is the various design parameters of this particular model. What are the design challenges, what are the design issues, what we have to think about, what are the do's and don'ts of developing this variant model has been studied in the next presentation. Thank you.